I welcome you for the second session on analysis of indeterminate structures. In the previous session, we were discussing on what is indeterminate structures and how to calculate the degree of indeterminacy. Now, in this session, we will be discussing on how to analyze indeterminate structures with one of the classical method, slope deflection method. In the slope deflection method is basically which is very much suited for analysis of continuous beams and rigid jointed frames. In this method, basically the end moments are expressed in terms of unknown slopes and deflection. These unknown slopes and deflection values can be calculated by applying the joint equilibrium condition, and this there will be a simultaneous equation with which solving those simultaneous equation we will be back calculating what are the unknown slopes and deflection. By knowing these values of slopes and deflection, we can calculate the end moments. Now, if since we are this method involves the solution to simultaneous equation, if we have more than three unknowns, solving it manually would be very difficult. But with the advancement of computer, this method has led to the development of stiffness matrix method of analysis, wherein the simultaneous equation will be expressed in terms of matrices and the solutions can easily be obtained. Nowadays, all the huge structures have been analyzed with the help of computer using stiffness method of analysis that we will be discussing in the fourth module of this subject. Coming to the assumptions or idealizations made in slope deflection method is in the joint in the frames are rigid, the angle between the members do not change after the deformation. The second and third assumption states that the axial and shear deformations are neglected as they are very small compared to flexural deformation in case of beam or rigid jointed frames. We have some of the sign convention before we start with the equations of slope deflection method. Here it has been taken the clockwise method. The clockwise moment is positive and anti-clockwise moments are negative. Rotation is, suppose if I just consider a simply supported beam which is subjected to a uniformly distributed load of magnitude say W. This beam will have a deformation like this. Now there will be a rotation at this joint A and also at joint B. Now here I'm measuring in the clockwise direction. So theta A is positive. That is what is being written. So theta B we are measuring in the anti-clockwise direction, because of which theta B is taken as negative. Sagging bending moment, beams which try to hog, those moments we are taking it as negative moment, and because of the application of downward load or because of the moment there will be sagging in the beam. This sagging we are taking it as positive. In order to calculate the shear force, we go with this sign convention that left up is positive and left down is negative towards the left of the section, and towards the right of the section, right down is positive and right up is negative. So this sign convention we will be using it. Now coming to the slope deflection equation, if you want to derive, so this is a general beam, a continuous beam, a portion of which is being considered. Now we can see that because of the loading, there is a deformation which is happening, and there is a rotation at support A as well as at support B. And this support B is sinking by an amount delta as well. Now here we will adopt a method of superposition and we will try to calculate moments because of all the uh, deformations, and we will finally will calculate the total moments which are acting at the ends. Now due to the externally applied load, because of the fixity, there will be a bending moment which gets generated, fixed end moments at both the supports. Now we are calling that as fixed end moment. I will take that as MFAB and MFBA and MFBA, which is at this is at support A and this is at support B. And because of the rotation theta, there will be a moment which is contributing this theta A is 4 EI theta A by L. And similarly, because at the other end it induces a moment which can be calculated as 2 EI theta A by L. And because of the rotation at theta b, here we'll have 4 ei theta a by L in the anti-clockwise direction, and here we'll have in the clockwise direction because at theta a, which will be equal to half of it, it is 2 ei theta b by L. Now, and because of the sinking of support, um, we'll have a moment which gets generated, which will be in the anti-clockwise direction here, that is why it has been taken as negative. It is 6 ei delta by L square, and here also it is 6 ei delta by L square. Both are in the negative anti-clockwise direction. Now, in order to calculate the moment at A, I will going to sum the fixed end moment at A, which is MFAB plus M dash AB because of the rotation theta A, and because of the rotation theta B, which is being taken as M dash AB, and because of the settlement of the support between A and B, it is being taken as M triple dash AB, which is minus 6 EI delta by L square. If I add all these four moments, I'll be getting what is the total moment which is acting at A, which is MAB. Similarly, if I want to calculate what is MBA, I'll have to add what is the fixed end moment at B, and what is the moment because of theta A, moment because of theta B, and moment because of the sinking of support. Now that I have taken it and I have added it all the components to calculate the total end moment which is acting, MAB is equal to fixed end moment at AB plus, because of theta rotation theta, it is 4 E I theta A by L at support A, and because of the rotation at support B, moment which is getting generated at support A is 2 EI theta B by L, and because of the sinking, which is minus 6 EI delta by L square. Now, MFAB, fixed end moments, plus I'll just take 2 EI by L as a common factor, which gives us 2 theta A plus theta B minus 3 theta by L. So this is our final slope deflection equation, MAB. Similarly, by adding all the parameters at support B, I'll be able to get the total moment which is acting at support B, which I am calling it as MBA, which is equal to MFBA plus 2EI by L into 2 theta B plus theta A minus 3 delta by L. That is, these end moments, we are expressing these end moments in the form of unknown rotations and this sinking of support delta. And by applying joint equilibrium condition, as I said earlier, suppose if I have a continuous beam which is going beyond, and if I have a member BC, now I can apply at joint B, moment MBA plus MBC should be equal to 0. That gives us simultaneous equation, which upon solving those, we will be in a position to find out what is theta B and theta C, with which we will be in a position to find out what is the end moments. Now, in order to go ahead with the further calculation, we should be in a position to calculate the fixed end moments because of different types of loading. So that will be taken in the next slide, wherein we have different formulas to calculate the fixed end moments. These fixed end moments can be derived by integration method or by consistent deformation method. Now, we'll take up this in this beam. We have both end fixed, which is subjected to a point load, which is a eccentric point load, which is at a distance A from left support and which is at a distance B from the right support. The fixed end moment at A is been taken as P into A B square by L square, and at the right hand side it is P A square B by L square. Now we can see that since the P load is nearer to joint A, the moment at joint A should be magnitude of the moment at A should be more. So because of which you can remember that it is P into A into B square. So B is higher than A. So this side it should be P into A into B square by L square, and the other side it is P A square B by L square. We are applying a uniformly distributed load since it is symmetrically loaded, the end moments at both the support should be equal. They are opposite. It is WL square by 12 in the anti-clockwise direction at A. You can take it as minus WL square by 12 because our sign convention is anti-clockwise negative and clockwise is positive. And on the right hand side at support B, we have WL square by 12. Similarly, we have formulas for all different types of loading, which has to be used in the calculation of fixed end moments. And in the next session, we will be taking up a numerical example with which we will be in a position to apply this slope deflection method to calculate the end moments, and finally we can draw shear force bending moment diagram as well as the elastic curve. Thank you.